Okay, so previously when we talked about the ideal gas, there's actually two assumptions. No interaction between gas molecules, and then the gas molecule doesn't have any volume. Once you move into the solution phase, there won't be the case anymore, right? Because right now, the distance between molecules become much closer, right? So they must have interactions. So you cannot use that definition anymore, right? So this is actually not going to work for your ideal solution. And the same, volume-wise, the volume is actually pretty substantial, right? So this too is not going to work. The new definition of your ideal solution will be the interaction between molecules actually do not change after mixing. Assuming today you have a solution A, you have solution B, and then you mix them together. In your solution A, the interaction you're going to see is actually between A and A. And in solution B, you only have interaction between B and B. But if today you mix them together, you're going to have interaction between A and A and B, and B and B. Okay, once you mix things together, different species is going to have interaction as well. So for ideal solution, what we're going to define is actually if the interaction between A and B is more or less the same as the interaction between A and the interaction between B and B, then we call this solution as ideal solution. So that's what we mean. The interactions between molecules do not change after mixing. Okay, so mixing is actually one of the very important process when we talk about the ideal solution. With that being said, another thing you can think about is actually if today you're looking at the volume of your solution A, okay, you mix with a volume of solution B. Since there is no interactions, so when you mix them together, the final volume of your mixed solutions should be equals to the simple sum of the two. Of course, many of the cases you see in your daily life is not like this, okay? For example, if you mix your water and the alcohol together, okay, assume the volume of your water is VH2O, volume of alcohol is actually VETOH. Final volume will be actually smaller than the sum of the two. And the reason is very simple, right? Because water and the ethanol, they all have hydrogen bonds. And it's actually going to interact with each other, and those things is going to attract them with each other, so that the final volume becomes smaller. In other words, this alcohol ethanol solution is not an ideal solution. Things we actually know that the definition of the ideal solution, we are actually using the mixing to define whether a solution is ideal or not. Then we should actually know about what is the delta G of mixing of your solutions, right? How do we actually get to here? So remember when we talk about the free energies of a gas system, the free energy G of your system can be described as G naught plus RT natural log P over P naught. The little circle at the top corners, that means actually it's measured under a standard condition, 1 bar, 25 degrees C. And then the free energy of a liquid will be G is equal to G naught plus B times P minus P naught. So how do we actually get the delta G of mixing? In other words, how do we actually prove this is the delta G of mixing? Okay, so what we're going to do is actually we're going to use gas as the example first. So initial and final. Let's say we have two components. Okay, one is called A, the other one is called B. Before mixing, you know the GA is simply equals to GA naught plus RT natural log PA over P naught. And then your GB is simply GB naught plus RT natural log PB over P naught. And final, you're going to have PA equals to GA naught plus RT natural log PA final over P naught. Your GB is going to equals to GB 0 plus RT natural log PB final of P naught. Let's put I over there, then you can see more clearly. So the delta G of mixing will be, you need to consider both. In the beginning, it's actually you only have this, and then that is actually your final state, right? And then if you want to calculate the delta G mixing of your whole system, what you should do is actually you want to do the number of moles of your species A times your GA in the final state minus your GA in the initial state plus MB times your GB in the final state minus your GA in the initial state. So the things that you know between your GA final and the GA initial, all these prefactors, they're actually all the same, right? So they're going to cancel out. Once you actually put these things into here, you are going to end up with NA times your RT natural log PA final PA initial plus MB times RT natural log PB final over PB initial. So in the finals, okay, you are mixing two gas. The vapor pressure of your final for a species A will be actually your PA final divided by your PA final plus PB final. And in the beginning, all of them is actually your PA. This turns, there's actually more fraction of your A. With that being said, then you know we can actually make this whole things a lot easier. So this is going to equals to RT times summation Ni natural log Xi. Okay, so this is going to equals your delta G of mixing. Basically, distance is going to equals to your Xi. Okay, and then I put the RT out, and then I just add them all together. That's why I got the summation sign times your number of moles. That is why I write this in the beginning. So we derive all these things from what? From gas phase, right? But we're trying to actually get the things into the solution phase. So how do you do this? We all know that this is derived from the gas conditions. If the system is actually at equilibrium, your mu I1 is going to equal to your mu I2. It means actually the change of your chemical potential in your gas phase will equal the change of chemical potential in your liquid phase. Even though you derive this one from your gas phase, it can be actually applied to your liquid phase as well. Things we know, when you mix these things, the chemical potential change is going to equal to RT summation Ni natural log Xi, right? So if you want to write out the chemical potential of each individual component, it must contain this RT natural log Xi term. In the end, we actually give a very clear definition of if you have ideal solution. The chemical potential of component I is going to equal to the mu I, sorry, here should be star, mu I star plus RT natural log Xi. If your Xi equals to 1, then your mu is going to equals to mu I star. More fraction equals to 1 means what? You have pure substance. So basically what this says is actually if today you are mixing things and then the chemical potential of that specific component will be the chemical potential of the pure substance. Then you do some corrections, and the correction terms is actually RT natural log XI. You should see that XI is always below than 1, right? Okay, so the second term is always negative. When you have multiple components mixed together, then the chemical potential of that specific component will equals to the chemical potential of the pure component minus something. Okay, and then that something is actually coming from delta G of mixing have these general terms. Then we just follow that form so that we define. If you have an ideal solution, then you should actually write out your chemical potential of component I in this way. If today you have ideal solution, the chemical potential of each individual component will always follow this relationship. So in many times, you will see some changes about the format, okay? Because sometimes people will actually write mu I equals to mu I start plus RT natural log CI. They want to use the molality. So molality is basically just number of mole of your solute over kilogram of your solvent. If that is the case, then these terms and that terms will not equal to each other. That means the mu I star here is not going to equal to the mu I star here. So this won't equal to each other. Sometimes people will also write as mu I is equal to mu I star plus RT natural log mi. So the m is molarity, which is defined as number of mole per liter of the solution. So in this case, your mu I start is not going to equal to the mu I start when you use CI or XI. Okay, all these things, even though they have the same format, this is not the same as that, it's not the same as this. Okay, so when you do the calculation, you want to be very careful about this. To conclude the things we have talked about so far, we are going to use this as our default format to describe an ideal solution. Okay, so this will be the definition that now you actually need to memorize it. If you want to describe a chemical potential of component I in a solution, the chemical potential of that will equal to your mu I start, which is the chemical potential of that pure substance, plus some correction terms, which has a form of RT natural log XI.